Hello guys, so welcome to our lab. This is lab 11, in which we're going to study the stability of common emitter amplifier with with the temperature. So basically the problem with temperature is that it changes beta. So beta is a strong function of temperature. So it's common that if you have a circuit and the circuit is running, the circuit will get hot. Okay, this will change the temperature, even if in the environment the ambient temperature is low. So you're gonna have heating up in the circuit, and this will change beta. Okay, so we don't have enough tool in multisim to do that. Okay, but we're gonna do that manually. So we're gonna study the stability basically at some beta. Then we're gonna tweak beta, so we're gonna increase it a little bit, such that we say that okay, the temperature increased, so beta increased, and check the new amplification. Okay, then we're gonna see, of course, as we learned in the lectures, that we with doing that, the amplification will change. Okay, because it's very strong function in beta. Then we're gonna put the degenerate resistance, which is basically emitter resistance, and as we learned in the lectures, this RE, okay, can make the circuit stable with temperature, meaning that the AV before the heating up and after the heating up, or when the temperature is low and when the temperature is high, approximately the same. Okay, so we're gonna test all that package today in this lab. Okay, so this lab is very similar to the previous lab. We have again very similar common emitter circuit, the circuit that we see here in the on the screen. Okay, in the beginning we're gonna study the stability with no RE, so we can have appreciation when we put RE and see it makes the circuit stable. So we're gonna put RE here, but we're gonna set its value to 0. How to do that? Basically just double click and put here 0. Okay, and press OK, of course. Click OK. Okay. Also, we're gonna change the beta of the transistor to 100. And again, how to do that? Just double click, edit model, and here it is, ideal maximum forward beta. It's 100. I already did that before this recording. Okay, so we'll not do that. So with that, we're gonna run the the circuit, measure the DC the DC values or the DC Q point, and find R pi, because we R pi to calculate AV, the theoretical value of AV. Okay, then we're gonna report here the theoretical value of AV. Then the measured value. The measured value come from here basically the oscilloscope. So we're gonna change the voltage per division, the scale of a channel B, the output basically the green one here. Okay, let's also reverse the background based on the values here that I'm showing on the screen. So 50 for a channel B and 500 microvolt for channel A, which is the input. Okay, now let's check the amplification. Okay, the amplification is to measure the amplification, just measure the maximum output and divide it by the maximum input. The input here is the red, the output is the green. Look, the output is green and the input on A is the red. So let's bring this to the max. So this is the maximum of the input. This is around 0.5 millivolt. Okay, 500. This is around 500 microvolt is just 0.5 millivolt. Now let's switch to the output. Select the trace. Let's go to the B, which is the output. Do the same trick. Go to the max. Here is the max. It's 86.3. Okay. Good. So the amplification will be around 172. Okay, so just record that in your mind. So when RE is 0 and the beta is 100, the amplification is 172. Okay, 172. Good. Now let's, measure the amplification. So let's now, imitate the situation in which beta is changing. The temperature changes, increases, so beta increases. Okay, and that's basically number B here. So the experiment 1 has A and B. So experiment 1 here, if you follow, you're gonna make the measurement at beta equal to 100. Then we're gonna assume in B here that temperature increases, so beta become 120 because it's beta increases with temperature, and then we're gonna redo the same steps again. Okay, so let's check. So first it changes the beta, so let's stop that. Double click, edit model, and make this 120. Easy. Oh yeah, it doesn't show the OK button or something. So to make this to make your change went into if go into effect, just click anywhere, and this will change or activate this button, so you can click it and this will change a bit. If we go back here, it's 120. Okay, we don't need, just press cancel, and that's it. So 120 now. Okay, and since we change it from the default, you have this asterisk here. This star will appear. That means this is not the default model of the transistor. Good. So now RE is still 0, but beta now become 120. That means you have some heat up or something. Let's now run again. Beta changes, beta increases, and if we look at the on the right here, if we look at the equation of the amplification, AV is directly proportional to beta, so it will increase. Of course, the input doesn't change, so if we measure the input again, it will be around 500. So let's just go to the, yeah, it's still 500 microvolt, around 500 microvolt, half millivolt. Now let's go to the maximum of the output on the channel B, the green. Now it's a change. Okay, it was 83, I think. Yeah, it was 83. Now it's 96. Let's say 97. Okay, but of course in your report you should report the correct value. I mean, without any approximation. But just for the sake of argument here, let's approximate it as 97. Now the amplification becomes 97 divided by millivolt divided by half millivolt, and that's basically, I think, 190, around 195. So in the beginning, when beta is 100, when the circuit just running, for example, we just start running the circuit, it doesn't heat up yet, the temperature is low, the amplification was 170. Now the amplification become 194. Okay, you might say that's better because we have more amplification. You might say this, but remember, one thing here to put in mind is that you have some calculation in your application, and you need the AV to be, for example, 170, and you designed your circuit to give you this 170. Other than this, you might have some problem in your circuit. So we always wanted to stick to our design. When I say 170, that means in the beginning, when beta is 100, that means you put your design, you put your effort, assuming that beta is 100, and this was good for you to give you the required or desired 170. Okay, so that's basically not desirable at all to have something in your mind, because you might use this 170 again in other calculation, in other part of the circuit. So you want stability all the time. Okay, that's for the circuit. This circuit without RE. Remember, RE here is 0. Okay, and from our lectures, we learned that when RE is, greater than 0, of course, we put it to make our circuit stable. Although that will make the amplification less, but we can, deal with this. Okay. So let's check now, experiment B and show how RE will make your amplifier stable, or its amplification is stable. So in here, it is exactly same steps that we did in the first experiment, except that we just will do it at 100. So we're gonna change RE now to 100 ohms. Okay, and again we're gonna have beta 100 measures the EV, beta 120 measures the EV, and if really RE will make your circuit stable, we should see same EV before and after changing beta. So let's check that. So I'm gonna first make beta equal to 100, beta edit model, bring this to 100 here, press anywhere, this will appear, click it, yes, yes, okay, okay. Now we should stop the simulation first. Okay, so let's now measure the EV. So we run. Yeah, look, we know from the beginning that RE will decrease the amplification, and the amplification decreased here. Okay, so this is EV. Of course, here the output is the green, but that doesn't mean the amplification is less than 1, or the output is less than the input. No, that just the scale is different. So if we change the scale, it will, it will become bigger again. Okay. So let's measure, now the EV. So still, of course, the input doesn't change. It will be around 0.5 millivolt or 500 microvolt all the time. Okay. So let's check. Let's do that. Let's check again that the input is constant, although we know that. So yeah, again 500 microvolt around. Then we select the output trace channel B and do the same stuff. Go to the max. 16 millivolt, 16.5 millivolt. Look, it was in the beginning when beta 100, it was 80 something, it was 83, I think, or 86. Okay, so now it's just 16. From 86 to 16, it's like it's divided by maybe 5 or 4. It's very, very high. I'm sorry, very low. Okay, or very high reduction. Okay, so now the EV is 16 millivolt or 16.5 millivolt over around 0.5 millivolt, which will give you 33. Yeah, 33. Okay. Now let's change beta to 120 and check the output amplification. So we're gonna stop the simulation, double click, edit model, and put this as 120. Click anywhere, change component, press OK, run again, and we should see approximately the same stuff. Let's check that. The input doesn't change, although we're gonna measure it again as usual. Still 5.5 millivolt or 500 microvolt. Go to the output now. Go to the max. 16 points. It was 16.5. It's now 16.7. So the amplification is 33.4. It was 33 when beta is 100. Now with beta 120, it's just 33.4. Very small increment. Okay, very small. So, and again, just to shed light and to connect the theory to the experiment here. Why this happens? Because in the beginning, if RE is equal to 0, this was the amplification. Okay. Now the new theoretical value for the amplification EV is this one here. And as you see, you have beta in the numerator and you have another beta in the denominator. So because RE now is not 0, so this will count. So if you have some change in the numerator, you have another change, another increase in the denominator. So they will cancel each other. Okay. In the beginning, you have just beta in the numerator. So just one term changing. Okay. There is no balancing from any other from any other term in the equation. Okay. So guys, that was basically the lab 11. Of course, it's a conclusion of lab 11 because you have many steps to do, like for example, reporting here the these values and calculating RBI. But that's the essence or the core of the work of lab 11. Thank you very much and see you in the next lab. Bye bye.